Welcome to this video on the topic of networks. In this video, we're going to have a look at something called a flow network and how it can be useful for modeling particular systems. Now, a flow network is simply a special type of network that we use to model the transition of information or items through a system. Now, such a system could be a road network and the amount of cars that can travel across it. It could be a network of water pipes and the water as it's running through the said pipes. Or it could be something like a labyrinth of computer cables and the data that gets transferred across said labyrinth. Now, if we draw our attention to this rudimentary diagram or drawing over here, what we've got is a simple one-way freeway. Now, the freeway itself on the far left, it's composed of 4 lanes. However, after an exit lane, it gets reduced down to 3 lanes. And then finally, after a merging lane, it goes down to just 2 simple lanes. Now, this sort of freeway system here can be modeled using a flow network. The flow network for this freeway scene here is seen just below over here. Now, you're going to see a number of striking similarities between this flow network and our directed weighted networks. Those being that this sort of network here, it's made up of arcs, and the arcs also have associated weights. Now, this is a flow diagram, so some of our terminology is going to change a little bit, and some of the meanings will change with it as well. Now, the first thing that's going to change is, well, we're not going to call these arc weights anymore. Rather, we're going to call them arc capacities. On top of that, we've got 2 new items within this network. We've got a source, and we've got a sink. Now, these are still regular nodes, however, they're going to behave in different ways to what we'd usually expect them to. The source within a flow network is a node with only outgoing flow, or in other words, it's going to feed all of the flow to the rest of the network. Similarly, with the sink, it's a special type of node in that it only has incoming traffic, or in other words, all of the flow within the network is going to be terminated at the sink. Okay, so now let's draw our attention back to the arc capacity. The arc capacity is going to act as the amount of information that we can get from, say, 2 nodes. So between this source node here and this node B, we're able to transfer a maximum of 4 units at a time, or at any given time, from this node to this node. From B to C, we're able to transfer a maximum of 3 units. And from C to T, or C to our sink, we're able to transfer a maximum of 2 units. Now notice the wording here, it says capacity. So by definition, what we're looking for is more capacity means more transfer or more flow. As a result, the network itself is going to be limited by the arc that has the lowest amount of capacity. In other words, it's going to be bottlenecked. Now the bottleneck in this instance is this number here. So this 2 is going to effectively reduce the arc capacity or the working arc capacity of all of the other arcs on this network to a value of 2. I'm going to denote it like this. So it's sort of like a fraction, but the bottom part is going to show how much capacity we have, and the top part is going to show the bottleneck of the actual path itself. Alright, so this is a nice simple example to dig our teeth into. But what about when the network itself that we're trying to model, or the system itself we're trying to model, is a bit more complicated than a linear network? Down here we have a slightly more complicated flow network. Now what you can see is that there are going to be multiple paths that lead us from the source over to the sink. As a result, there's going to be multiple pathways in which the flow within this network may travel. Now what we're going to do is we're going to determine how much flow we can get from our source of this network over to our sink of this network. In the example up here, we're able to get a maximum flow of 2 flow units. But let's have a look how much we can get here. Zooming in, what I'm going to do is I'm going to use to determine the amount of flow I can get from here to here, I'm going to use a bit of a brute force strategy in that I'm just going to examine as many paths as I can come up with until hopefully I can get as much flow out of this network as possible. Pretty much I want to saturate the amount of flow that's coming out of the sink, the amount of flow coming out of the source, or I want to saturate the amount of flow capacity I have heading towards the sink over here. If I saturate this over here, as in I use all of the capacity up, or if I saturate it over here, then I know that I won't be able to improve upon this. So first thing I'm going to do is I'm going to pick the simplest path, and for me, the simplest path, in my opinion, is from the source over to node A, then from node A down to the sink. I'm going to identify my bottleneck within this path, and it's going to be the 17, because 21 is much bigger than 17, so we can only get a flow of 17 units across this edge here, and at this point in time we can only get 17 out of this edge. However, lucky for us, we've got more than one pathway. We can go from source to A. We identify our bottleneck. We have 4 units left over here. We have 4 units available here, but we only have 3 units on this edge over here, this arc. So the maximum we can get here is 3, 3, plus 3 to get 20. Alright, let's look for another pathway. We go from here. So from our source to node A to node B, down to node C, until finally getting to our sink. From there, we're bottlenecked. We've got 16 units of flow we can use here, 9 over here. We've got 1 unit left here, and also just 1 unit left here. So our bottleneck on this pathway is now 1. So I'll go plus 1. We'll go plus 1 here, just move the 3 over. We're going to get 1 across this arc, and then we're going to get 1 at this point in time across here. Okay, so we've been able to saturate this particular arc over here, this arc here, and this arc here. Let's see what we can do to saturate this arc. Looking at our next pathway we could logically take, we have from node S down to node C, and then from node C we can go up to node T. Now the bottleneck on this path here is we've got 18, but 18 is bigger than what we have left over here. We've only got 15 units of flow left here. So what we're going to do is we're going to take 15 from here, and then we're going to consume 15 from here. Now we could try and figure out a way to try and somehow get the 3 units of flow that are left over here, flow capacity left over. But what you can see is that our network capacity, or our edge arc capacity, our arc capacity that's leading into the sink is now saturated, in that there's no more capacity left over to fit any more flow through it. Consequently, what we've found is something called the maximum flow. And it's going to be a value of 17 plus 3 plus 1 plus 15. That will be 20 plus 16, which comes out to be 36 units. So maximum flow being how much flow we can get from our source to our sink within this flow network as seen here. And we calculate this by simply summing all of the capacity that's in use that's heading into the sink itself, in which case we get 36 units for this network. Let's go down and do another example, slightly more challenging. Example 3 here, we have another network, and what you can see is there are multiple pathways from the source to our sink. Now, as you saw in the example above, I didn't really have an algorithm to solve it, rather I just used a strategy. The difference between a strategy and an algorithm is that an algorithm's a definite way in which we can find the solution to a problem. A strategy is just a sort of fixed steps we use that will sort of lead us to the end result, but it's not going to guarantee success. Most of the time we will get success. So reason we're using a strategy as opposed to an algorithm is that, simply put, the algorithms themselves are quite complicated, and you don't need to use them as such when the networks aren't overly complicated. So this is a good starting point. So what I'm going to do is I'm going to use my favorite strategy of I pick the easiest paths first, and I try and saturate all of the capacity across the arcs themselves. And only once I exhaust all of my simple pathways will I start trying to direct flow through other pathways or more complicated pathways. So the simplest one I like to use is above the top first. Identifying my bottleneck, it's going to be 15 here. On the right side, I'm using 15 units of flow. We still have capacity over here and over here, so I want to try and use that up. So I'm going to go from this node. I'll use up my units of capacity or flow by identifying the bottleneck first. So we've got here, which is limited to a value of 3. This is also a value of 3. I've got 5 here. I've got 5 here. As a result, I'm limited to the smallest number. So we'll go 3 here. But that saturates the arc anyway, so I'm happy with that. So we've got 2 units left over here that we could use potentially, and 2 units left over here. So we'll see how we go. Let's try and use them up actually. We'll go, as a result, we're going to go plus 2 here, plus 2 here. So we've been able to completely saturate being we've used up all the capacity over here and here, which is also nice. Alright, now we need to look for a new pathway. This is our working edge at this point in time. So we'll use that. We'll take the simplest path possible to the sink, and voila. Now next step is we need to identify our bottleneck. So we've got 23 here. This will come out to be 21, and we've got 21 here. So we'll go 21 plus 21 plus 21. And thus, the strategy is now finished because we've saturated this and this. So we've saturated all of the flow coming out of our sink. Now to be able to determine our maximum flow, we simply need to sum the capacity or the utilized capacity going into the sink here. So maximum flow is equal to 15 plus 3 plus 2 plus 21. And it comes out to be 41 units. Thus concluding the maximum flow within this particular flow diagram here, or flow network.